Okay, hello everyone. So let's continue where we left off. Okay, so um, we determined that the water doesn't flow through because the pressure of the oxygen in the water above the solution is the same as the pressure of the outside atmosphere pushing on the water, so the water level doesn't change. Okay, so we can actually describe this. The pressure that collects above a liquid, we can call it has a special name. This is called the vapor pressure. Right? So this is called the vapor pressure of the liquid. So when vapor pressure equals atmospheric pressure of when vapor pressure of a liquid equals the atmospheric pressure of the surrounding environment, that's when we have a phenomenon known as boiling. So when the pressure is equal there, you can actually there's the equilibrium between so the process of gas molecules going back into the liquid and gas molecules escaping from the liquid, and now it's going to break that kind of dynamic there, and then eventually you reach a point where the pressure is going to always increase as more liquids approach the gas phase, because the pressure above the liquid and with the atmospheric pressure, they're the same. So as soon as each molecule now escapes into the gas phase, that pressure is always going to be greater than is going to kind of pretty much tell you that the liquid wants to escape. So as you boil something, eventually, when you reach that equilibrium state, or that state where the vapor pressure is equal to the atmospheric pressure, the liquid is going to just keep on boiling, because as soon as the liquid escapes the vapor, as soon as the gas molecules escape into the atmosphere, the vapor pressure decreases because it escaped. So when it decreases, it's going to want to boil off more gas molecules to replace the difference in pressure. So that's why boiling occurs at atmospheric pressure. But sorry, that was a roundabout explanation. Did anyone have any questions about that phenomenon? We can talk about it more. But that's boiling. When vapor pressure equal to the atmospheric pressure. Okay, and we'll talk more about that when we talk about solutions. Okay. All right. So now let's use this analogy here. Let's use the let's do an example where we take into account the water vapor above solution. Okay. All right. So let's calculate the number of grams of oxygen that can be collected by displacing water from a 250 milliliters bottle at 21 degrees Celsius and 746.2 milliliters of mercury. Okay. So we're going to assume that the gas we collect in the experiment is saturated with water vapor. Okay. So the vapor pressure of water at 21 degrees Celsius is 18.7 millimeters of mercury. So what this means is that our total pressure here equals the pressure of oxygen plus the partial pressure of the water vapor, and that's going to equal our total pressure that we observe, 746.2 millimeters of mercury. Okay. So we know the water vapor, right? It's given to us as 18.7 millimeters of mercury. So we can solve for the pressure of oxygen directly. So the pressure of oxygen equals 746.2 millimeters of mercury minus the partial pressure of water, which is 18.7. So that will give us a value of 727.5 millimeters of mercury. Okay, and if we convert this to atmospheres, this would be equal to, so we do 727.5 millimeters of mercury times equals 0.957. Atmospheres. We could probably actually take it to 1 more sig fig, though, so we should probably do that. So let's do it 572. Okay. Here we go. All right. So now our temperature here is going to be 294 Kelvin. And then we can use our volume here. We're going to change our volume as well. So volume equals 250 milliliters. So 250 milliliters. So we're going to assume that it's just 3 sig figs here. And then we're going to convert this to liters, which will be 1,000 liters per, 1,000 milliliters per liter equals 0.250 liters. Okay, so when we do all that, we're going to solve for moles and then convert that to grams of oxygen here. Okay, so using ideal gas law, we can solve for moles. 294 Kelvin. And we get, but maybe let's first do this a little bit differently. 0.9572 times 0.250 divided by 0.08206 divided by 294. Okay. So we get 0.0099992 mole oxygen. Okay. And then we'll take this value here. So as long as you follow the rules of sig figs for every step, I won't take points off for rounding. But if you but you could also keep extra digits in intermediate answers, like for the moles of oxygen, and but your final answer should be in the correct sig figs. So as long as you follow either of those guidelines, I'm perfectly fine with it. So we can collect this much oxygen right here. So 0.317 grams of oxygen. So see, we can take the, if we collect oxygen gas over water, we have to assume that total pressure has water vapor in it, so we would consider this contribution of the vapor pressure from water. And I will always give you that information in a problem, so you don't have to memorize any of that. Okay. Oops. All right. So let's move on here. Okay. So the third homework assignment, it will cover gases. So we'll get more practice with gases and also in lecture. Okay. So now let's talk about the kinetic molecular theory. So the assumptions we have been making for the ideal gas law and why we could use it has been made based on several of these assumptions. So let's talk about it. So it's a theoretical model that can explain like these observations we make for gases, how they behave and how they act in a certain environment. So these are some things we should understand about gases. I wouldn't really stress memorizing it. I would try to stress how to apply this theory into how we understand gases. So understanding how gases behave. So gases are composed of a large number of particles, right? So there's a lot of gas particles. So they behave like spherical objects in a state of constant random motion, right? So they're kind of like, like if you were to run into a field filled with like pollen and there's very windy, it kind of moves kind of like those things, or like a bunch of flies or fleas, they're moving really fast and they collide with with whatever is in their vicinity. That's how we kind of describe pressure of a gas in a container. They're always colliding and they're always moving very fast. So we say they move in a straight line until they can collide with another particle or the walls of the container. So we say particles, they have what we call the mean free path, is basically the path a gas particle takes until they collide with another object. So we say they kind of move in a straight line until they collide with something else, where they then are probably deflected or they change their course or path. Okay? So even though the gases are spaced out, we say the particles are much more small than the distance between the particles. So even though they're small molecules, they're very small compared to the distance between them. So in this case, when we see gas particles, we assume that they have no volume, or most of their volume is empty space. So they don't occupy much volume themselves, but the bulk of the gas, they will occupy the volume of the container. But the volume of a gas itself, so they're very small particles, so they don't occupy much volume individually. So that's what that is saying, okay? And we assume that since the gas molecules are moving so fast as compared to liquids and solids, which are much more in place and they're not moving to any point within the container, they have no intermolecular forces, or there's no force of attraction keeping the particles together. So that's why gases tend to escape into the atmosphere and dissipate pretty much, and you can no longer recover it or store it as soon as it escapes. Okay, so it's very hard to do that. All right. So, and then we have what we call point 5. Collisions between gas particles are perfectly elastic. So we assume that no kinetic energy is lost between two gas particles. So all the energy is transferred completely between two gas particles during a collision. So energy is conserved between the gas particles. But we know in reality that's not true. Just take any example of two objects colliding. They do not transfer complete kinetic energy. So some kinetic energy is lost as heat or lost as other forms of energy. So that's one stretch of the limitation of this theory, because we know collisions are not perfectly elastic. So elastic just means if two things collide, they'll bounce off in different directions, or they'll change their directions, but they'll still have the same speed. Um, we know that's not really true, because if you think about how a basketball, well, I'll go into this example, but you think of like if two cars collide, right? They're not going to bounce off and have the same speed. They're going to take some damage, and that damage, the damage is caused from the loss of energy as heat, and so the cars will no longer move as fast as they were going before the collision, and they'll eventually slow down because they have suffered a car wreck. Okay? So, and then that points us into assumption 6. So the average kinetic energy of gas particles, they don't depend on anything but the temperature. So how fast a gas moves, so kinetic energy is basically the energy from the motion of something. So the gas particles, the speed of a gas particle depends nothing, so I wouldn't say speed, but the kinetic energy a gas has depends on only the temperature of the gas and nothing else. It doesn't have to do with their speed, their mass. It only depends on the temperature. So it may sound weird that kinetic energy, even though a gas particle, it should depend on the kinetic energy, but if we think about it, two particles will have the same kinetic energy. One will just move faster than the other if they have different masses. So it's kind of a balancing act here. So so we say all gas particles, their kinetic energies only depend on the temperature and nothing else. Now, the speed at which they move is going to be different, because speed depends on mass of an object. But for kinetic energy, it's going to be, it only depends on the temperature. So if two gas particles are at the same temperature, they may move with different speeds, but they'll have the same average kinetic energy. So that might not make much sense now, but we'll talk more about that in a bit. Kinetic energy is influenced by two things, not only the velocity, but the mass. So an object can have a high mass and low speed and still have the same energy as a small object with a high velocity. So it's totally possible to have the same kinetic energy. If so, say you have a large object moving very slowly, and then a small object moving very fast. It's possible to have the same kinetic energy, and usually in this case, gas particles, they're so small that we don't consider their difference in mass to be very how we say, it won't be very different. So kinetic energy in this case, it only depends. We're saying average kinetic energy. So on average, it'll only depend on the temperature. Now, their actual kinetic energy, it'll probably depend on the mass and how fast they're moving, but on average, they'll have the same it'll only depend on the temperature, because the temperature is what influences the temperature. By definition, temperature is the average kinetic energy of your sample. So the temperature of anything is just measuring the average kinetic energy of your sample, and when we talk about gas particles, it only depends on the temperature. Okay, so they'll all have some average kinetic energy, and we'll talk more about what this means for gases in a bit. Okay, so sorry for dragging on for too long about that. Okay, so in the next video, we'll start talking about what this means in terms of objects having kinetic energy. So I'll see everyone in the next video. Okay.